these together, or you doing it separately?
So if you've got a multiple lens system, with a multiple lens system, the magnification is the product of the two magnifications. So if I've got, let's say, two lenses or a lens and a mirror, it's pretty not important which ones they are. So I have an image here. Let's just assume that the first is a lens, then a converging lens, which causes the image to be right here.
Right, it's parallel.
So this is, we'll just call it P1 and Q1. So the magnification for the first lens, the magnification 1 is negative Q1 over Q1.
Right.
The magnification for, when dealing with a second lens, we treat this as the object. And so we have this P2 here. And it produces, we'll just say it produces an image here. So that would be Q2. So the second magnification would be negative Q2 over P2. And then the total magnification of the two lens system is that times that.
Okay, that's all I needed to
Yep.
know.
Any other questions at the moment?
No.
Oh, this is about the Thursday test.
Yes.
Will questions from this current test that we took today will quiz, will that also be on that test?
Yeah, matter of fact, there probably, I suspect there's gonna be a question very much like that on the test.
Right, I was wondering. And, will it also be stuff on like the illumination, stuff like that on there?
Yeah, basically it's from the illumination chapter onwards.
Alright. And are we putting stuff, are we like, getting material today that's also gonna be on that test?
It is also fair game for that test.
Alright.
Yeah, there's much less time between the final test and new material. Well, 8-week course and all. Other questions at the moment?
All right, so you said to calculate the magnification of the two lens system for number 5 is basically multiplying the two together.
Yes. Had you already done it?
Yes.
Okay.
But I didn't do it that way.
Oh, okay. You get the same answer? You said you didn't do it that way. I mean, you got it, but you have an answer, so I was wondering if you have the same answer as if you did it both ways.
I don't like that much.
Okay.
I have a question about number 3. It says, what do you suppose the actual focal length is? But how are we supposed to find that?
Let's see. If you know the manufacturer's focal length, what's the error between it? If you don't know it, what do you suppose is the actual focal length to justify your answer?
We weren't given the focal length.
Right, okay. If you looked at the other packages, I don't know if you did, but let me just read out some of the focal lengths that are there. Oh, that doesn't have one on there. Focal length 250 millimeters. Negative 74 millimeters, 69 millimeters, 46 millimeters, 82 millimeters, 154 millimeters. So focal lengths typically are given and to the nearest single millimeter.
So I was like, I just put the focal length is probably between 15 and 20 centimeters.
Yeah.
Because
You don't think you can narrow it down more than that?
I don't, from what, I mean, I don't, like from.
I mean, if you feel it's
that
just.
we did 15, I guess, because it goes from 14 to 16 on this.
Yeah, I got it. I'll put it.
I mean,
I got percentage of, close to
Your
8%.
percentage of what?
It says have the percentages up here on there.
If you know what,
Error, the percentage error between.
right, if you know what the actual
We don't.
manufacturer focal length, if you don't, then just come up with your best.
Yeah, I just put a
Education
percentage,
speculation.
yeah.
right, I mean, I got values from 17 to 14, just,
Just do the best you can.
okay. I guess I'll just take the average of those.
Okay.
This is interpretation. Stick it in.
One stack is fine, just put it right there. Other questions that come up?
Is this due on Thursday, lab?
I'm good with that. Anything else? So there's this big debate, going back to, well, I guess in terms of classical physics starts with Newton. Although some might make an argument to slightly before that, as he claims he stood on the shoulders of giants. But there's a debate over the nature of light. Wave or particle.
Oh, I'm getting into quantum theory now?
No, not really. I mean, here's the bit of quantum theory. The answer is both.
Yep.
Or either, depending upon how you look at it. Okay, that's the quantum bit. We're still sticking in the classical realm at the moment.
That's chapter 38.
37, actually. 38 is relativity. Or quantum, I think it's relativity, and then the one after that's quantum. It's possible they stuck relativity and quantum all together. So, Newton was a big fan of the particle theory, and Huygens was a fan of the wave theory. And if it were dark in here, and you look at a stream of light coming through the window or the door, Newton saw that you had a very clear image here. So if I had a window, you have a very clear image of light coming through, which would indicate it is a particle, because particles tend to travel in a straight line. If you actually notice, look on the edges, it's never actually a really sharp contrast there. It gets kind of fuzzy in this area, which is an argument potentially for wave. But if light were a wave as it comes through the window, potentially it would then just sort of spread out. So I was about to say definitive test. I guess definitive test in terms of classical theory goes, it gets turned on its head about 100 years ago.
Wouldn't the light bulb be an example of wave because it's in every direction?
Why could it not shoot particles in every direction?
Because it's always shooting them, I guess.
It's always what?
Shooting them, I guess. I mean, it's always, like the light is always on. Or let's say a light is always on. It's always moving in every direction.
It still could be shooting particles in every direction. I think you could go with an argument with that, though, is if you're far enough away from a light bulb, then if it's particles traveling in a straight line, then I see it here, nope, I don't see it, I now see it, because particles do go in a straight line. Although I think the person in favor of the particle idea would go that the light bounces off something, and so you would always see it no matter where you were. But the actual evidence, the big evidence in terms of that seemed to set the record straight for 100 years was the double slit experiment. So Young's double slit experiment, which was the early 1800s.
Is this the same guy as the Young's modulus?
I think it is, but I'm not 100% sure. At that time, these guys were dabbling in so many things. So I'm just speculating it's the same guy, but I don't know for sure. It's like Bernoulli. There's 5 different major Bernoullis in mathematics for about a several hundred-year period. So if it's a Bernoulli thing,
I guess that's your lifetime, I guess you're real good at math.
yeah. Double slit experiment. There's also a single slit experiment. If you've got a gap between your fingers, which most people do, not everyone does, and you look at the light, and you can see these little dark lines that are in between, in the gap. That's a quick and dirty single slit experiment. And you just keep your fingers, do you not have a small little gap here?
Oh, yeah, yeah.
The smaller the gap, but making sure there still is a gap, the more apt you are to see it. But there's still little black lines that are right between there, at least I see it with my fingers. And that is basically a single slit experiment. So if it's a particle, what I would expect is if I shone light through here, I'd get a whole bunch of light here and a whole bunch of light here. So basically, if I plotted brightness would be the brightest there, and then there. Should be equal. So basically, particle theory would say that I got 2 bright spots here. Now, there's a little bit of a spread to it because the particle could bounce off the edge here and then basically go into some other, it will not go directly, but be slightly off. What a wave says, so just imagine that I have a wave coming through here. So if you picture a water wave, that works too. Wave is going to get to this, and then it's going to start working its way through here. So I have these 2 waves coming through here, and the places where they meet like this, I have constructive interference. And the places where one is troughing and the other one's peaking, so right here, this would be destructive interference. And what I would see against the wall there would be, the brightest spot would be in the middle. Then there'd be a less bright spot and then a less bright spot, but I'd have these alternating, I'd have bright spots, brightest in the middle and get less bright as you go, but I have multiple spots. Now, they did not have lasers at the time. I'm not quite sure how they actually, what light source that they used in order to be able to get basically experiments. So Newton was late 1600s, and so it's 140, 150 years later, the experiment is actually done. So let's actually do the variation of this experiment. Any other lenses that I'm looking for? That'll work. That's what I want. All right, this is known as a Cornell plate. And it's got a whole bunch of single slits and double slits in it, and I suspect you can't really see it particularly well. Maybe if there's a light behind it, you could see the fact that there's seems to be gaps in it. So let me slide this down. And the double slits are over on this side. These are single slits here. And I'm hoping that we can see this, and we'll turn the light off for better view at some point. Really?
Red light ain't working too good.
There we go. Nope, we're gonna have to darken the room. And that is. Can I grab a second laser? Because I had one that was working just fine. I think it's the one I picked up here. There we go. It doesn't really want to work. All right, you can see that spread there. And you got those dark bands. I don't know how well so all of you can see that. Do you see the dark bands?
Yeah.
Yes.
Nick, I guess you're farthest away.
Yeah,
That was not a convincing.
they're there, I think, I don't know what I'm looking for.
On the sides, the dark bands on the side.
Yeah, so basically, there's two things going on there, but you got a bright spot here, and then there's a bright spot here, less bright, dark band, and then you've got bright spots again, and then dark band, and so on. Part of it, you've got a double slit, and then within that, there's a single slit diffraction pattern going on. All right, let's do a little prediction here. We'll come back, we can predict what the wavelength of light is, and show that we get close. But it's physics, it's never gonna work out perfectly. But that was the huge evidence that it's not a particle, and that was believed for the next 100 or so years. We'll touch just briefly a little bit more on quantum here. The idea that light behaves like a wave was held together for a long time, and then came along what's called the photoelectric effect. So if I have some sort of surface here that with a lot of electrons that can get tossed off if there's enough energy, and you basically shine a light onto it. In some situations, you get electrons to basically get enough energy to come off of the plate here, and then you have a detector over here which detects the electrons. They notice that sometimes electrons don't come off. And basically what the experiment said was that there's a threshold frequency. So if you're below a certain frequency, no electrons are going to get shot off the plate. If you're above that frequency, some will. Now, if it were a wave, if light was purely a wave, then if I shine this light at it, new particles come off, well, I can increase the energy in a wave just by increasing the amplitude. I make it brighter. But if I'm below the threshold, making it brighter, in other words, increasing the amplitude, does not make more electrons come off, does not make electrons come off. However, if I'm above the threshold, making it brighter, I will get more electrons off. But if I'm below, I can't. And so that was the big evidence for the fact that it was actually a particle. And so this wave-particle duality is a hallmark of quantum physics, where everything seems to behave like that, including electrons. There was an experiment where they shot the electrons through a double slit experiment. You shoot a bunch of electrons through, and over here you have some surface that will basically light up when the electron hits it. If electrons are purely particles, I get a whole bunch of electrons here and a whole bunch of electrons there. So if I take the electron, shoot it at it, what I have is a whole bunch of electrons here in the middle, not as many here, fewer there, and so on. And so electrons seem to behave like waves. So then they decided to put a detector here to see which slit the electron was going through. And when they put the slit there, the pattern changed completely, and the pattern was now, I have a whole bunch here, and I have a whole bunch here. So just by the act of observation, we changed the electron into a particle. Fun quantum stuff.
So basically, it's neither a wave nor a particle, but at the same time, a wave and a particle.
It is both until you observe it, and then it's one or the other.
But we have to interfere with it to observe it. Because this is at a scale where you can't see an electron. So you have to put a machine or a tool.
Right, there's gonna be some interaction there.
Right. So it's not necessarily just the act of observing it, because we are interacting with it at some degree. It's not like we're looking through a window, seeing it outside, and we have no control over it at all.
But the observation, by viewing it by sight though, I mean, we get into some nuances and some debates within physics. Viewing by the naked eye is generally considered seeing it.
Yes,
and
but
observing it.
But
And
we can't see it by the naked eye, though. That's the thing. Like we can't see individual electrons.
okay, agreed.
So we have to put a machine or a tool to detect it for us, because we can't see it ourselves.
Right.
And whatever we're doing at that scale is going to interact with the electrons to some degree.
Okay.
It's not like the electrons have knowledge of us that we're observing it.
That we know of, right?
I don't think they do. But
I don't think so either.
I mean,
I'm with you.
so it's not not just that we're observing it that's changing it. We're actually interacting with the electron to some degree.
I think that's what observing it means.
Right.
We have to measure it some way.
Right, I mean, all they're doing here is measuring, well, it's going through one slit or the other. They're looking at, presumably as the electron goes through, there's a change in the potential. This is just checking if the potential drops or